We are looking last week and this week on the foundations of modern science, kind of the presuppositions, how it operates. So this is sort of my starting point. When I think of science, and you may be like me, I tend to think, first of all, of what are known as the empirical sciences, and what we know as the scientific method. Several weeks ago, we kind of walked through this kind of a thumbnail of the basis of the scientific method, how science operates. In the scientific method, empirical science is predicated on using our senses, and the goal is to try to understand the natural world that's out there. It follows a very particular methodology called the scientific method. It begins with sort of just observation of the natural world. And then as you observe the natural world, certain questions start to arise. You know, why does this happen? How does this happen? What's that about? And with the scientific method, you begin to think of, well, what are some possible explanations? What are some ways that we might be able to explain the phenomenon that we're looking at? Technical terms for these are called hypotheses. These are sort of the underlying thoughts as to what might possibly give us an answer. You follow that by devising experiments, and then by running the experiments, and then mining the experiments for the data. And this is really how you test the hypotheses. And then, of course, it's never very simple, so you follow the data, which means that you're going to have to refine the hypotheses, because if it doesn't work, there could be a lot of different reasons. It could be that your hypothesis, it's not that the hypothesis is bad, but every hypothesis has many, many features to it. So you have to tweak that, figure out what's going on. And you do testing, and this goes on and on for a while, constantly refining till you get what seems to be some good data. Then, if the data looks good, it supports your hypothesis, you've tried to knock the hypothesis down with everything you could and you couldn't, then you need to kind of verify that what you're doing is correct, verify that you do indeed have what's called a theory. And so this involves publication, getting it out there into the larger scientific community, having other scientists look at it. Other scientists maybe run the same experiments or maybe other experiments. This is a process simply called peer review. And if it holds up and it survives the peer review, then we have something referred to as a theory. Now, this approach is used in many of the classic sciences: biology, chemistry, geology, and physics in the sense of classical physics, not in the sense of theoretical physics. We're going to talk about that tonight. This is a little bit different, but classic physics, the physics that would do experimentation. Just a reminder, in empirical science, there is no truth, there is no proof. Just a never-ending quest to understand the universe and how the universe works. Constantly refining our understanding of nature. Now, we may be less familiar, I know I definitely was, with the fact that there is a second methodology that's used by science today. It's a methodology that is not empirical. It uses an entirely different approach, an entirely different method. The second approach has become increasingly important, especially in the realm of physics, particularly what we would today call theoretical physics. Theoretical physics is essentially based on this second methodology. The second approach is simply known as pure mathematics. Pure math proceeds by using a different methodology than traditional science, one that does not deal with empirical data. It does not run traditional experiments. Pure math pursues math for its own sake. It uses logic. It is deductive rather than inductive. And in pure math, you get a lot of language and comments about aesthetics and beauty. The beauty of an equation carries a lot of weight because the beauty of an equation often means, or it's language about the fact that the equation works. other words, you don't pursue pure math for any practical or real world reasons, at least in the pure sense here. Pure math deals with, among other things, numbers that are not real. And that may sound weird, but here's an example. The square root of a -1. This is a number that does not exist in any real sense in the world. You can't go out in the world and find the square root of a -1. So it doesn't exist in that sense. But it is a number that works within mathematics. You can do equations with it. You can solve problems with it. And so there's a whole category of mathematics called irrational numbers or unreal numbers that you can work with. It turns out that pure mathematics, simply using the mind as a tool, gives us real insights into the physical world. Discoveries in pure math have opened entirely new vistas, particularly in the realm of theoretical physics, and in cosmology and other areas too, but particularly physics. It has led to some of the most remarkable discoveries of our time. This, in turn, has led to much of the technology that we enjoy today. Later, we'll be talking about quantum physics, but quantum physics in particular is based on pure math, and quantum physics has given us pretty much all of the technology that we have today. The idea that lies behind the mathematical approach to science is utterly mind-blowing. Pure math is predicated on the belief that this is a technical term you see in the literature, there is a pre-established harmony that exists between the nature of pure math and the structure of the universe itself, the structure of reality. There's a connection between pure math and reality. This is because nature or reality has a mathematical quality to it. Most of what you're going to get tonight comes from this book, The Universe Speaks in Numbers. Fabulous book. Cannot speak more highly of it. It requires no math background whatsoever. It simply tells the story. It gives the narrative that I'm going to try to present to you tonight. The universe and math, again, this is technical language, are braided. They are interconnected. Even more mind-blowing, it turns out that human beings, and I'd never heard of this earlier, human beings have an innate sense of numbers. This is a sense that science says is independent of language, memory, or reasoning. It's a sense that is intuitive. This is why some like James Clerk Maxwell, Albert Einstein, and many others have made their greatest leaps in science intuitively. They just had a sense that this was the direction to go. This is the thing that needed to be done. And they went through that. We'll see that 2 or 3 times in tonight's presentation. Further, it turns out that pure mathematics has been a key, if not the key, to unlocking the secrets of the universe, particularly in our own time. This is because the laws that govern the universe are written in the language of mathematics. This is a statement that's said over and over again across several centuries by most of the great scientists you can think of. The deepest ideas in math, particularly in pure math, and this is kind of a radical statement, but this is the statement, invariably have consequences in physics and manifest themselves in matter. The deepest ideas that come out of mathematical equations invariably have consequences in real world physics and manifest themselves in matter. We'll see that tonight. It seems that the universe is knitted together by mathematics. Now, shifting metaphors, we might say, as this book does, that the universe speaks to us in numbers. A number of scientists have said that. Theologically, you could even say that God speaks through math. By the way, this is something that Galileo said, and this is something that Albert Einstein said. Albert Einstein was not religious in the sense of a traditional structured religion, but Albert Einstein was extremely spiritual and did believe in God. And this is the part that he resonated with. The idea behind this approach to math is that if we can understand the math, we can understand the universe itself. The reality that lies behind and beneath everything that we see and experience. This is what math gives us access to. Or to quote Albert Einstein, if we can understand pure mathematics, we can understand the mind of God. This enables physicists to predict the results of experiments even before the experiments are done. We'll see in the history tonight that a lot of times you would have experimentation first, and then you would have math try to make sense of what you discovered. We're going to see here that that is flipped. You're going to have mathematical equations be predictive. They're going to say you're going to find this, you're going to find that, and then you conduct the experiments, and very often you find out, or you find exactly what the math said you would find. Professor Nimer Akana-Hamed, theoretical physicist, some of you may know, says this in his book: we can eavesdrop on nature, not only by paying attention to experiments, but also by trying to understand how their results can be explained by the deepest mathematics. You could say that the universe speaks to us in numbers. It's his quote that became the title for that book. Paul Dirac, theoretical physicist back in the first generation, says this: if you're receptive and humble, mathematics will lead you by the hand down an unexpected path that leads into new territory, where one can set up a new base of operations from which one can plan future progress. Here he's probably speaking specifically of quantum physics. Now, we're going to do a little history here, sort of trace forward. The idea that there's a pre-existing harmony between math and the real world has been around a long time. It is something discovered by the ancient Greeks. You've heard of the golden mean, algebra and geometry. Well, Apollonius of Persia, commenting on his math theorems, which seemed to have no value, he was actually, his book was on conics. If you take a cone, a three-dimensional cone, and slice it at different angles, you get different mathematic forms. And so he was experimenting with that, and other people, I think, were criticizing him because it didn't seem to have any value to do that. And this is what he had to say: the theorems are worthy of acceptance for the sake of the demonstrations themselves, in the same way as we accept many other things in mathematics, for this and for no other reason. In other words, it doesn't have to have a practical consequence. It has value simply by being valid math. The old joke in that is, when you say to somebody, shut up and crunch the numbers, doesn't matter if it's practical. Two scientific traditions that we use today both come to us from the Greek world. One is the empirical, which believe that the world can best be understood through our senses. This is commonly associated with Aristotle, but it actually predates him. It includes a variety of people like Leucippus, Anaximander, Democritus, Lucretius. Lucretius's book, The Nature of Things, was discovered around the time of the Renaissance and blew a lot of people's minds. And then, of course, Aristotle. The other tradition that comes to us from the Greeks is the rational. They believe that the world is mathematical and could best be understood through the mind, not the senses. This included Pythagoras, Parmenides, Euclid, Zeno, and Plato. So two traditions, both being anchored. But it was not until the 1600s and the work of Copernicus, Kepler, Galileo, Newton, and of course many others, that we were actually able to do better than the ancient Greeks back in the 3rd, 4th, 5th centuries BCE. In the 1600s, what made the difference was scientific instruments. And these instruments, like the telescope and the microscope, keying on optics here, discoveries in the realm of optics, began to open our eyes to the world. It was much bigger than we had thought, and it was much smaller than we had thought. About this same time, we began to embrace the idea that nature was rational. That had always been there. But this began to move into science in a major way. In 1623, Galileo made a startling and a prophetic statement. This is a statement about the relationship between math and the physical universe. This is what he said: mathematics is the alphabet by which God has written the universe. And so this idea, the language may shift, but this idea becomes central. It would be Isaac Newton who would show that what Galileo said was in fact true. Newton sought to understand rationally the entirety of God's creation. Under Aristotle, we had one set of laws for what's happening on Earth. We had another set of laws what happened, beyond the moon. So we didn't have one set of laws. He wanted to understand rationally everything. In 1687, he published Principia Mathematica, which explained mathematically the motion of matter everywhere, from the Earth to the cosmos itself. The mathematical explanation is known as the laws of motion and the law of gravity. A little interesting footnote here: the book is many hundreds of pages long, but the laws of motion are 2 pages. The rest of the Principia is the law of gravity. It's by far the more developed. His law of gravity was based on equations and mathematical formula. It was not empirical. What Newton produced was the first mathematically based but empirically verifiable framework for describing the real world. Principia Mathematica literally changed the world. We're going to hear that several times tonight, but there's points in history when this does happen. Voltaire famously commented, "Newton is our new Columbus. He has taken us to a new world." So you get the idea of, in that generation, what an impact his work had. Newton's laws made heaven and earth part of the same universe. And the word universe comes out of this. For the first time, we have one set of explanations for everything. However small, however large, the laws of motion, the law of gravity operates the same, without difference, everywhere. In Newton's physics, everything was mathematical. This is where we get the idea of the clockwork universe of the 1700s. Now, for 2 centuries, no one dared to question Newton's worldview. I'm sure there are some who did, but effectively, nobody successfully proposed any kind of an alternative. So from 1650s to the 1850s, Newton's physics reigned supreme. But in the mid-1800s, things began to change. About this time, Newton's physics pretty much explained everything. But in the language of the day, some scientists began to say, well, Newton's physics explains everything, but there's a few clouds that we haven't quite explained yet. Well, those few clouds turned to be huge in terms of what happens in the future. Scientists were seeking to understand aspects of the world that could not be explained by Newtonian physics. We're going to see this happen several times. A revolution was coming. A revolution that was going to be grounded in math. Newton's science was grounded in math. The science that would replace Newton would be grounded in math. The key players at the outset, at the beginning here, are Michael Faraday and James Clerk Maxwell. Now, the revolution begins with Michael Faraday in the 1820s. Remarkable man. Just reading about him, I tripped several breakers mentally. Faraday was attempting to understand the nature of electricity and magnetism. At this point in time, they were understood to be two entirely different forces, unrelated to each other. Now, Faraday was not a mathematician, but he was one of the greatest experimenters of all time in science. His experiments in his lab fundamentally undermined Newton's physics, or Newtonian physics. For Newton, for example, space was an empty container, and forces only traveled in straight lines. That's how Newton understood it. But Faraday demonstrated that space was not nothing, it was in fact something. Space was a repository of energy and for the transmission of energy. We see this in his famous demonstration of iron filings on a magnetic field. Here, although you can't see the magnetic field, with magnetic filings, you can see that the magnetic field is there, and it is not Newtonian. Faraday's experiment showed that space was filled with fields and forces. Even though we couldn't perceive them through the iron filings, we can show they're there. He also showed that electric and magnetic fields were circular. They acted all around. You see this by putting a bar magnet down and how the iron filings arrange themselves. This violated Newton's idea that all forces operated in straight lines. Faraday also demonstrated, and this was huge, that electricity and magnetism are related to each other. An electric current near a compass causes the compass to change direction. When the needle of the compass shifting to the right angle to the wire, when the current's on. So you can simply see that. So something's going on. Electricity impacts magnetism. Faraday also discovered that electricity could generate a magnetic field, creating the world's first electromagnet. Faraday then demonstrated that magnetic force could produce electricity, and in doing so, he created the first electric generator, called the dynamo back then. Faraday also demonstrated that electricity could produce magnetic force. In so doing, he created the electric motor. I mean, what comes out of his research is just mind-boggling. As a result of his experiments, Faraday came to believe that electricity and magnetism were really two forms of a more fundamental force. The force, of course, would be electromagnetism. Through further testing, Faraday demonstrated that electric force was an inherent power in matter. Even things that don't conduct under the right conditions can conduct. Everything, all matter, can conduct electricity. Some are just better conductors than others. And that this was communicated particle to particle. Now, this is not empirical. This is one of those intuitive leaps of Faraday. This is what he thinks is happening. Later, these particles would come to be known as electrons, and we now know those particles that he thought might be there, that he was in fact right. The particles that carry electric force. Faraday even demonstrated that a magnetic field could shift the polarity of light. It's called the Faraday effect. If you've seen any of these really expensive windows that you can actually make them opaque or transparent by throwing a switch, that's the Faraday effect. Thereby showing, through the Faraday effect, that all of the known forces in nature at the time, electricity, magnetism, and light, were related to each other. It was also Faraday who introduced the idea that energy or force existed in fields or waves, not particles. This idea did not come directly from his experimentation. This is one of the great intuitive leaps in the history of science. He intuited that that's what was going on. Now, although Faraday knew some math, he was not primarily a mathematician. He was not able to develop his intuitive leap about electromagnetism into a fully fledged mathematic theory. That had to wait to the next generation and a new man, James Clerk Maxwell. Maxwell was a mathematician, and it's Maxwell who used math to make sense of what Faraday had discovered empirically. The experiments came first. Maxwell's trying to bring some kind of order to the experiments. Like Newton, Maxwell sought to understand the world using the smallest possible number of laws. Math was the tool to do this. Specifically, he wanted to understand why the abstractions of math, pure math, applied so well to the concrete reality of the experimental. So what Galileo had said centuries earlier, Maxwell is trying to work that out. He's trying to comprehend it. In 1873, he published a treatise on electricity and magnetism. What Maxwell did is he translated Faraday's ideas and the results of his experiments into the language of mathematics. He used equations to show that electric and magnetic forces were different manifestations of the same phenomenon. They're not two different things. They're two aspects of a greater thing. Specifically, Maxwell's math demonstrated that electricity and magnetism were both forms of Faraday's fields, something we know today as electromagnetism or the electromagnetic wave. Maxwell's EM theory brought mathematical order to a mass of experimental observations that Faraday had done over decades. Maxwell's EM theory fundamentally changed our understanding of reality. He was the first to recognize that the foundations of our physical universe are imperceptible to our senses. He helped us realize that there are in fact two different levels of reality. There's one that we can access through the empirical, we can touch, we can feel through our senses, and access through experimentation and the empirical sciences. But there's a deeper level of reality that we cannot access empirically. It expresses itself through the language of mathematics. This deeper level of reality gives rise to things that we now know and use every day. Maxwell did all of this not through the use of empirical experimentation, but through the use of mathematics, pure math. Today, Maxwell's EM theory is held to be the foundation of the modern world. Later, we're going to deal with Einstein, having an entire session on his work, but we need to touch this briefly here because Maxwell and Einstein are connected. By the late 1800s, theoretical physics was using only math without any reference to empirical data, which, by the way, raised the hackles of some other scientists. This is the world and the stage that Albert Einstein stepped onto. Einstein gave credit to Maxwell for making his own work possible. This is a quote from Albert Einstein. Maxwell's ideas did more than give a new understanding of electromagnetism. They gave a profound insight into all the laws of nature. With James Clerk Maxwell, one scientific epoch ended and another began. I owe Maxwell more than anyone. I stood on Maxwell's shoulders. Einstein's approach to physics would be like Maxwell's, using pure thought and mathematics rather than empirical data. Einstein's experiments were thought experiments rather than those done in the traditional lab. In 1905, Einstein changed the world again using only thought experiments and pure math. He produced the theory of relativity. Over 10 years, first the specific theory of relativity and then the general theory of relativity. Again, these came not from the lab, but from equations, from pure mathematics. Einstein believed that theoretical physics could make progress through math because the laws of nature are best written in mathematical language, even without the stimulus of any empirical results. He believed that you could use pure math to understand reality because reality was mathematical. This is what he wrote in 1936. The eternal mystery of the world is its comprehensibility. The very fact that underneath the complexity and diversity of the universe is a relatively simple order, that very fact is nothing short of a miracle or an eternal mystery. I hold it to be true that pure thought can grasp reality. There seems to be some deep connection between mathematics and physics. I would like to express the connection by saying that God is a mathematician who has constructed the physical world in such a way so as to bring out beautiful mathematical features. Empirical science is anchored in its observation and facts. So it deals with what some people refer to as an isness of the world. The things that we observe empirically are there. They is. There's an isness to it. Theoretical science, the other branch of science, anchored in pure math, also deals with an isness of the world. But the isness is not grounded empirically, it is grounded mathematically. Others thought Einstein was nuts to use only math. Wolfgang Pauli, a name you're probably familiar, one of the great pioneers of the early 20th century in quantum physics, famously said this: I should congratulate you, or should I say send condolences, that you have switched to pure mathematics. I will not provoke you to contradict me in order not to delay the death of your current theory. The current theory he was critiquing was general relativity. What Einstein was doing ran counter to 250 years of empirical science based on observation, experimentation, the scientific method. But Einstein was right. Since the 1970s, physicists have been using pure thought, bolstered by mathematics, to systematically unlock the secrets of the universe. Today, the standard model of particle physics, we'll come back to this later in another session, but the standard model of the basic building blocks of the universe, quarks, leptons, bosons, the Higgs boson, this entire model is based on Einstein's approach using pure math to tell us where to go, and then use experimentation to verify it. This model, the standard model, stands as a monument to the success of this approach to science. The standard model is built out of ideas that first emerge out of math. But then you have to spend a lot of money with some very powerful instruments like the CERN before you can actually empirically test it. Time and again, the math predicted what would be there. And empirical experimentation had proven that the math indeed was right. It was true. Pure math has predicted black holes, dark matter, dark energy, and gravity waves. All of these have now been empirically verified, some just very, very recently. Today, pure mathematics has led to theories that lie at the very edge of science. Later, we're going to have an entire session on string theory and loop quantum gravity. But again, this is math, and it's out there on the edge. These things currently lie beyond our ability to verify experimentally. Again, we're going to explore that in a later session, but some of the literature on this says that with things like string theory and loop quantum gravity, if we can ever empirically verify these, it's going to be centuries in the future before we would have the technology. And that is if we can ever do it. All of this predicated on that little observation made by Galileo 400 years ago. Mathematics is the alphabet in which God has written the universe. The next 2 weeks, we're going to swing back to the faith side and deal with the reaction, both positive and negative, of faith to the rise of science. But for now, we are going to stop